Guys, so today we're going to talk about how to fit distributions, or we talked about how to fit distributions last time. Now we're going to talk about how to check if that distribution that we fit to our data is a good one, if it's a good fit. So you can imagine we're given a data set, and that data sets we might think for various reasons that it's normally distributed or log normally distributed, just kind of depending on what people have done in the past or what we know about the data. We can visualize it using histograms. And then ultimately we need to fit a distribution to the data so that we can do things like hypothesis testing, which we'll talk about starting next week. Testing, are these two data sets different? Are the means different? Calculating probabilities and quantiles using these data sets. So there's a lot of reasons we want to fit distributions. And today we're going to talk about how to check how well they fit. So the first thing we'll talk about is a quantile plot, or a QQ plot, also known as probability paper. And probability paper is an anachronistic term. It comes from back in the day when we didn't have R and our computers to do statistical analysis. We had to plot our data on probability paper, and it just has special axes that allows the data to kind of be stretched out and flattened in a way that we can evaluate how well it fits to a normal curve or a log normal curve or something like that. So we don't actually use probability paper anymore, but you'll see references to it out there. So that's a visualization that we can use. And then we'll talk about the chi-squared goodness of fit test. So chi is this X, curly Q X here. It's a distribution. It's actually related to the distribution of variances, but you can also use it to test the goodness of fit of data. So we'll look at that. So the first thing we're interested in is this quantile plot, or a QQ plot. And what that means is we're comparing quantiles of data, so basically the ordered data, to the quantiles from a certain distribution if they came from that distribution. And that can be any distribution. We're going to be talking about the normal distribution because it's the most basic QQ plot that we can make. So what you do is you plot your observations, you sort them from small to low, or low to high, right? So here's our lowest observation, and then here's our largest observation. And then we plot what the theoretical quantiles would be. This is expected. So this is observation and then expected. And expected comes from the theoretical distribution. So where would these points fall if they came from a log normal distribution? And that's how we plot this on this axis. So let's actually talk about what quantiles are. So a quantile is evenly distributed points along a distribution. And the way they're evenly distributed is we have, if we're interested in, say, dividing this up into 10 quantiles, this distribution, then we're going to find the area or the probability between those intervals such that the area is equal. So they're not going to be evenly distributed if this is Z, so if we're dealing with a normal distribution. The quantiles won't be evenly distributed, but the area between these curves will be the same. So if, say we're having, let's see here, I think I did 8 quantiles. So we want to distribute this across 8 even areas. So we would figure out basically the probability or the area between this using the CDF such that the area in this interval is the same as the area in this interval, is the same as the area in this interval, and so forth. So each of these areas is 0.125, and that way we have, let's see, I think it ends up being nine values that give us these equal intervals inside. So quantiles have different spacing along the z-axis such that there's equal area. And the quantile refers to values of the distribution. So often we're dealing with z values or the z-score. Other distributions, you have different values. And just as a refresher, percentiles are values along a distribution with a certain percentage of observations or area falling below. So the 50th percentile for the normal distribution is the same as the mean, and it has 50% of the area below it. The 99th percentile has 99% of the area below it. Quantiles are percentiles. They just happen to be evenly distributed. So it's a kind of percentile. Okay, so let's talk about how to actually make a QQ plot for a normal distribution. First, we take our data, our observations, so X observations. We'll plot these along the Y-axis. Sometimes you'll see it flipped. And we'll order the observations from smallest to largest. All we do is just sort them. So step one, sort your observations. And that's what you'll plot for your Y values. The second is we want to create a vector of quantiles from the standard normal distribution using the order of our observations. So this is going to be our X values. I'm calling it X norm, or the quantiles along the X axis for our norm from our normal distribution. So if n is equal to the number of observations, say we have 50, and we'll go through an example in R where we do that. So 50 observations. This is the code we put into R, and I'll show you that, how it plays out. First, we're going to do repetition of 1 over n plus 1. So we're going to have 51 chunks, and you could think of these as our intervals between which we're calculating the area. So we're going to have, n1, n2, n3, and so forth, and n. So these are going to be the area underneath that normal curve, if we have a normal distribution under here, right? And so we need n plus 1 boundaries to calculate that area, because we're going to have n areas that we're calculating. So those are the equal distributions of probability.
And that's a 1 in the numerator?
Yeah, 1.
Okay.
Yeah, so 1 over n plus 1. And that just says, okay, let's divide that distribution up into n times, right? So we're going to have n chunks evenly, and that even spacing is going to be n plus 1. So that's just going to be the probability. So if we have 50 observations, then it's 1 over 51, and that's going to be the spacing that we'll have to calculate the equal intervals of probability, or the quantiles.
That 1 over n plus 1, is that like the area per quantile?
So what that is, yeah, so you could think of that as the area or the probability. So in this case, I showed you if we were to divide it up into 8 chunks. So that's 1/8 right there for the area. In this case, this would be 1 over 51 if n equals 50, or if n equals 7, and this would be the area. Sorry, here. This gives you the bounds, and then the area is going to be between these 2 points. I'll show that. I'll show you visually what it looks like in R after I go through this. So this gives you a vector of the kind of points we're going to evaluate probability. We're going to do the cumulative sum. So that basically gives us, okay, we start off with say 0.125, and then 0.25, and then so forth all the way up to n. So that's going to give us our cumulative sum, and then we plug those into the Q norm function, which is a quantile function, and Q norm spits out the values, in this case z values, because we're assuming the standard normal distribution. So you give Q norm probabilities, it spits out z values, and then that will give us the points along this that we evaluate the probability between. Okay, so making our QQ plot. The next command is going to be just plot xnorm and xobs. So these are the quantiles from the normal distribution. These are just our sorted observations. And this is just running through that example of, so if n equals 7, then rep n plus 1 to n gives us 1/8 n times. We sum them up, so 1/8, 2/8, all the way up to 7/8. We don't go quite to 1. We put that into Q norm, and then Q norm spits out these z values for us. So that's what that QQ plot would look like. So this could be our quantiles x norm, and then so this would be x observations. And if it's from a normal distribution, it's going to fall along a line pretty well, a straight line pretty well. And we'll look at some examples of how it might diverge from that.
Hey, Joel, a quick question.
Yeah.
What are those Q norms, like the -1.15, -0.67?
So these are just z values
Okay.
from the standard normal. So what this is saying is if these observations came from a normal distribution, given their order, these would be the z values associated with those observations. This is where they would fall along that PDF, those values would. And if there's a linear relationship between these z values and your ordered data, that means they follow a normal distribution pretty well. So now we're going to fit a line to these data, and it's very straightforward. We just need to find a slope and an intercept value. So to do that, we're going to use the first and third quartiles. And quartiles are simply, if we had 4 quantiles, a quartile is those intervals. And so that would be 0.25, 0.5, 0.75 are the quartiles. That divides any distribution up into 4 chunks. So the first quartile is going to be 0.25, and the third quartile is 0.75. That means 25% of observations or area fall below the first quartile, 75% of observations or area fall below the third quartile. So to do that, we will first sample our observations. And we can use the quantile function. X is our observations. And we just tell it, here's my observations, give me the 25th and 75th percentile value from that. So it'll do interpolation, right? If you had 100 observations, it would just find the 25th or 26th, I'm not sure exactly, observation, and then the 75th observation if you had 100. But rarely do we have a perfect 100 samples, and so it'll do linear interpolation usually to back calculate those values. And then for our x values, we're going to just find the 25th and 70th percentile from the standard normal distribution. And those will be z values or z scores. So they should be the same because the standard normal distribution is symmetrical, and this one will be negative, this one will be positive. So now that we've got 2 values, basically you have y1 and y2 from your 25th and 75th percentile, and you have x1 and x2. So you have 2 points with a coordinate associated with each. We can find the slope, and this diff function just takes the difference between the two. So you do diff y, diff x, and that gives us our slope. And then we can do using just the equation for a line, y is equal to mx plus b. We get b is equal to y minus mx. So we're just solving for the intercept here. Which is b. And so we just plug in, it doesn't matter, we can plug in one value from y and one value from x. So y1, x1, the brackets just means sample the first value from the y object, and the y is a vector with two numbers in it. And then x1, x bracket 1 just means sample the first value of x. We plug in our m, and then we can calculate our intercept. So now we have a line, we can plot that line using the command AB line. I'll show that to you in R in a minute. And we can put that line through the data, and then we can see how well that data follow along the line. I'm going to open up R and just run through that with you guys. Okay, so I have this R script. I'll post it on Canvas. And what I've done here is created using the R norm function, so random normal. I'm taking a sample of 50 with a mean of 7 and a standard deviation of 0.25. So I'm going to create just a random sample from the normal distribution. And then we'll fit a PDF. We'll plot the histogram. Okay, so we'll do a histogram. Bring this over. Okay, so there's our histogram, kind of normal, not super normal, a little skewed. Obviously, it's just a sample of 50. Then we'll fit a PDF to that histogram and plot it. So we're using the D norm function, density of normal, to with the same mean and standard deviation, and then we'll just plot that over. So that's what the fitted normal distribution looks like using the method of moments. Well, actually, it's not the method of moments. That's from the original. We could use the method of moments by taking the mean and standard deviation of that sample. So let's just do that real quick. We'll do X bar. And then S is going to be equal to the standard deviation of X. So let's plot that as X bar and S. So that's the distribution fitted to the data. And then the original distribution was that previous line. Okay, so we can kind of use this method of moments and kind of plotting the PDF over the histogram to see how well it fits. You know, I'm not totally convinced at this point, so let's do a QQ plot and see what happens. So to do that, we're going to see here, plot content. Okay, this first thing, what this first code does is it shows you what quantiles look like of a normal distribution. So I created a vector for Z. I put Z into the standard normal distribution density function to create my Y values. I said, okay, I want 10 quantiles. So I'm plotting Z scores over here and then the density distribution. So this is the standard normal PDF for the normal distribution. And then I do those quantiles. So I do that. So first I do the percentiles. So this gives me the values of percentiles if I want to create 10 quantiles. And so that's just what this looks like. So it goes from 0.09 all the way to 0.91. And then I plug those into Q norm, and then Q norm gives me the Z scores or the Z values associated with these increasing percentile values. So let's just see what Q norm looks like. Okay, so Q norm, it's symmetrical at negative 1.33 all the way to 1.33. But the spacing is a little bit different, and that's what you can see here with these vertical lines. So all the area in between these lines and underneath the curve is equal. So obviously they get thinner towards the center, they get wider as we move far out. And then as we go over here, we get a much bigger area. This plot goes a little bit below 0, so that might be confusing. So I'm going to just do AB line H equals 0. That's where the cutoff really is. So these red lines show you how the spacing of quantiles. It's a little bit hard to see, but you can see how the spacing of quantiles changes because we're trying to get equal area. Okay, so back to our QQ plots. I'm going to ignore this. In the book, they talk about plotting position, which is rank over n+1. That's exactly the same thing we're doing when we do this cum sum function right here. So we're just going to ignore that. So n is my length of x. How many x values do I have? I port that in ascending order, so from small to large right here. So we start at 6 and we go up to 7. And then I plug that cum sum rep into Q norm to get my quantiles. So rep over 1 over n+1 n times. That gives me, this is basically 1 over 51, 50 times. I take the cumulative sum of that. And it goes from 0.019 all the way to 0.98. I plug that into Q norm to get my normal quantiles. And then I plot that. So what I'm plotting is, let me make this square so we can actually see that a little bit better. So I'm plotting is for my y values, it's the normal quantile, or sorry, for my x values, it's the quantiles from the normal, and then my x values are just the sorted x data. Now there's an easy way to do this in R. We're kind of walking through the manual way just so you can understand it. In R, we can use this function right here. So QQ norm. So QQ norm is, it will plot your data. You just give it your x values. And it kind of already labels, say, if your sample quantiles, your theoretical quantiles. And then it labels this as normal quantile. And then the command QQ line, you give it, again, your observations, and it fits a line to the data. So you can determine how well that observation fits. So you can see there's not a really good fit in the tails, and usually the tails is where you're concerned about the fit. This code right here just goes through the fitting of the line. So calculating the slope and the intercept of this line. So you can go take a look at that, and we'll have it in a lab too. Okay, so that's quantile plots. It's a quick way to see how your data, oh yeah, I'm supposed to show some examples here. So let me pull those up. And I will show, let's see here. Okay, there we go. So this is just our the handout that we have from Against All Odds video. And what it's showing is how different distributions, this is that egg data, what they end up looking like when we plot them on a QQ plot. So here's a distribution, it's pretty symmetrical. It doesn't have kind of weird tail behavior, and the tails in the histogram are here. And it lines up really well on that line that we fit to the data. So that's a good fit. Here's one where the data is kind of funky. You get this weird thing going on in the tails. So that would be a distribution that's, let's see if I can find that distribution. Yeah. Here's some distributions that are skewed. So this one is skewed to the right. So we have more density on the right-hand side, and we have this long tail. And so that ends up giving you a distribution that's a little bit curved and doesn't quite fall on the normal distribution line. So maybe something like a log normal distribution, a skewed distribution would be a better fit. Here's one that's skewed to the left. And so when we say skewed to the left, it simply means that we have a heavier tail on the right, or sorry, on the left-hand side. Here we have a heavier tail on the right-hand side. So it's skewed to the right. And this kind of looks like a bit of a concave upwards type of fit to the data. Again, not normally distributed. So it's good to kind of go back and forth. The histogram is always a great way to visualize your data. And then we have this QQ plot to also see how well the line fits. Any questions before we get into the chi-square distribution? Okay, so for the chi-square distribution, it's called the chi-square goodness of fit test. And what we do here is we're comparing our observed, so the observed frequencies of observations to the expected or theoretical frequencies from a distribution. And when we refer to frequencies, we're referring to basically something you would do in a histogram. So when you make a histogram, you bin the data, you count how many observations fall in each bin, and that gives you your histogram. So say we have n observations in a sample and we want to see how well they fit the normal distribution. And we break those samples up into k bins, calculate the frequency of observations, O sub I, in each bin, k sub I, so each bin is, there's k bins. And then we compare the observed frequencies in each bin to what we would expect from the normal distribution. And from the normal PDF or CDF, we can obviously calculate the area and then translate that back to, or a probability, and translate that back to an expected frequency from the normal distribution. So this is kind of the visualization of what that looks like. Here's our histogram, these values right here. So observation 1, observation 2, observation 3, and so forth. Here's our bins, right? So 6 bins. And our data, we just bin them up and we count the observations. Now we can go to our PDF, so we fit a normal distribution to that. And then we can calculate the area between those bins, within those bins, right? And that area then should be similar, if it is the same distribution, to the observations that we have in our histogram. So we're basically comparing the area of a discretized, chunked up normal PDF to a histogram. And this goodness of fit metric, it's like chi-square goodness of fit metric. I'm just calling it GOF for goodness of fit. And then this is the chi-squared symbol, is equal to the sum of the observations minus the expected frequency. So observed frequency minus expected frequency squared divided by expected frequency for each bin. So it's summed across all the bins. So we calculate the value of this goodness of fit metric, and we'll note that theoretically this goodness of fit metric follows a chi-square distribution as our sample size goes to infinity. And it has a certain amount of degrees of freedom that kind of specifies the shape of that distribution. And we'll talk about degrees of freedom in a minute. So the reason why this test works is that this metric right here follows a chi-square distribution. Then we can use the chi-square distribution to test if our observations are in fact different from the expected values we would get from a normal distribution or any other distribution. So this works, this whole method works for any distribution, not just normal distribution. So we can test, and we haven't talked about hypothesis testing yet, but this is kind of our first introduction to it. We can test whether the distribution of our data is significantly different from a normal distribution or any other distribution by calculating the probability that our goodness of fit metric value that we calculated up here, what's the probability of that occurring along the chi-square distribution? And is it extreme enough such that are these observations that different from the expected frequencies, the observed frequencies that different from the expected frequencies, such that we think that, you know what, this just isn't a good fit. So what that might look like is, here's our chi-square distribution, and we set some arbitrary value. Usually it's a probability of 0.05 in the tails here. And so there's a value of chi-squared, like a critical value here. So there's a critical value of chi-squared such that there's 0.05 area above it. And we can compare the value from our goodness of fit metric to this critical chi-squared value and see, is it smaller or bigger? If it's bigger, then we're over here and we're saying that the distribution of observations is different from the distribution we're comparing it to. If it's less than that critical value, then we can say, well, we can't reject our null hypothesis, which is that it's from the same distribution. So we can say it's probably from the same distribution. So the null hypothesis in this case is that the distribution of observations is not different from a normal distribution or whatever distribution we're comparing it with. Our alternative hypothesis is that the distribution of observations is different from a normal distribution. So you can imagine it's a pretty weak test because there's a really good chance that you're going to be over here, right? It's going to be, the observations have to be pretty different so that you're on this side of the line and you're significantly different from what we would expect to see. Usually when we do comparisons of means and we say, is the mean of sample 1 different from the mean of sample 2, you want the means to be so different that you're on this side of that critical value. So usually that's a kind of a harder thing to prove. So we can just walk through how we do this in R. And I'll, maybe I'll just, I don't know how helpful it is to do this in R, so we can kind of go back and forth. I'll share my whole screen and then we'll kind of refer to this sheet. This sheet kind of tells you a little bit more what's going on. So I would recommend writing this down. This is kind of like a reference for you, just to show you the steps that we take. So I'm going to share both that and my R screen. So hang on here. Let's try to do that. Okay, so here's the second section of code here. We're going to compare the frequencies of our observations using a histogram to the observed frequency, or to the expected frequencies or theoretical that we would get if we fitted a normal distribution to it. And again, this test can work for any distribution, not just normal distributions. So we'll stick with the same sample of X, and we'll make a histogram of X. So we've already done this. Now the histogram function, it creates an object. And so because I said, do the histogram of X, but store it in this object, I then get an object up here called xhist, which I called it. And within that, there's a number of different things. We can kind of treat this as a table, and we can use the $sign to get these different components out of it. Okay, so the first component we're interested in is the bin values. And so that's under breaks. So I say x bins is equal to our histogram object, $breaks. And let's just look at what that is. So these are the break values. That starts at 6.4, and then it just gives you those equal values all the way up to 7.4. So that gives us the bounds of our data, and it's equally spaced bins at 0.1. Now we want the counts in each bin. And so that's under the counts component of X histogram. So X bins, and then I'm calling those XO for observations, the observed frequencies. So within each bin, we then have our counts. So 2, 2, 2, 4, 5, 12, 8, 8. So these are our counts. And you'll note that our X bins right here has 11 values in it, and our observations has 10, because the bins give us the brackets. So we have n+1 bracket values, and we have n values within, or it counts within each bin. All right, so the number of bins, so the length of our observations gives us the number of bins. And now what we want to do is compare our observed frequencies, which we have stored in XO, to our XE, or expected frequencies, if we fit that normal distribution to it. So I'm going to do, let's see, X bar here. So we're going to use the method of movements to fit this normal distribution to the data. And what I've done is I said, okay, here are my X bin values, so 6.4, 6.5, all the way up to 7.4. I'm going to plug that into the CDF. So P norm is my CDF. And I want the cumulative probability values associated with each of these X values on the bins. And here's the mean and standard deviation. So let's just run that. And so it gives me the increasing probability. So if I were to plot that, let's just visualize that real quick. We'll just plot that, and then we can do I'm just going to plot the CDF for you guys. We'll do X, F, X, and Y. Okay, so there's our CDF. And then if I want to show, just kind of visualize what we're doing here, we'll do AB line H is equal to P norm. So now what we're doing is we're putting all those bin values in there, and we're calculating the cumulative probability associated with those. So here's our bin values, and here's the cumulative probability. So now
to calculate the observed, or sorry, the expected frequency that we would get from the normal distribution in each of those bins, we can simply take the difference between this value and this value, and that gives us the difference in cumulative probability, which just gives us probability, which we can get as area if we multiply that by n. So what this is we're just taking the difference between each of these cumulative probability values, multiplying that probability by n, and that gives us the expected frequency. So here's our expected frequency, and here's our observed frequency. So in the first bin, we would expect to get about half an observation, we got 2. In the second bin, we would expect to get about 1.6 observations, we got 2, and so forth. So far, I'm not thinking this is a great fit. Here's our chi-squared metric. So we're just summing the observations minus the expected frequencies squared over the expected frequencies. And these are all vectors of the same length, so it'll do that operation. And then there's our chi-squared statistic value, 6.6. Okay, almost done. So now we have a chi-squared metric. We compared our observations and expected frequencies. And I'll come over here to our, this is what the chi-squared distribution looks like. Here's our goodness of fit metric, 6.6 over here. Let's see what that critical value is. And we can use our, let's see here. We'll use Q chi-squared. So chi-squared, this is just the quantile function for chi-squared. We'll give it degrees of freedom. I'll explain that in a minute. And then we'll give it the alpha value. So if alpha is equal to 0.05, then we'll put 0.95 in here. So we want to get the chi-squared value associated with cumulative probability of 0.95, and then we'll use those degrees of freedom. So that critical chi-squared value is 14. So we're below, our chi-squared value is below this. We get true, okay. So degrees of freedom, this just basically refers to the shape of this influences the shape of the chi-squared distribution. You can think of it as a parameter. Degrees of freedom for this particular problem is defined as the number of bins, k, minus 1, minus the number of parameters that we're trying to estimate here. Because it's the normal distribution, we're estimating the mean and standard deviation, so that's 2. So we end up with a degrees of freedom of k minus 1 minus 2, which is 7. Obviously, you could bin your data differently and get a different chi-squared value. So this test is sensitive to how you bin your data. So we just tested if our chi-squared value, the difference between our observations and expected frequencies, is that less than the critical chi-squared value. We found that it was. Let's calculate the p-value associated with this. So I put my chi-squared value in, I find the cumulative probability at that degrees of freedom using the p chi-squared value, and then I do 1 minus to see what's the probability that 46%, this is the probability that our chi-squared value is significantly different. And it's below our critical value, so we reject, or sorry, we accept the null hypothesis, saying that in fact it's the same. And then to visualize that, our goodness of fit metric was over here, our critical value was over here, and so because we had such a low goodness of fit metric, we cannot reject. We have to accept the null hypothesis. And so their distribution of X is not different from a normal distribution. So those are 2 ways to evaluate goodness of fit.
come back and share my camera. And what we'll do is have, I'm going to try to make it a little bit shorter lab where we will fit distributions using method of moments and as well as maximum likelihood. And then we'll look at these quantile plots and do the chi-squared test to kind of see how well those distributions actually fit the data. I couldn't find a built-in function in R. I'm sure they exist where you can just do the chi-squared goodness of fit test. There is a chi-squared test that exists, but it's a different kind of test. It's for a different problem. So if you see chi.test or some chi-squared.test or something like that, you know that it's not the same chi-squared goodness of fit test. And it won't necessarily give you the answers you're looking for. So the best way to do it is just the kind of method that I outlined here with that R script, at least as far as I know. Granted, I didn't spend a lot of time looking for it. But we do have those built-in QQ plot functions. Any questions, y'all? If there's no questions right now, then we can talk about homework or the lab.
I had a question on the, it's that second half of the lab, and it's the derive and plot the PDF and CDF of the flow capacity. And it's following the log normal distribution. So I don't know how to apply the log normal. Like, I know what the equation is for the PDF of a log normal distribution, but just kind of confused on how to apply it in R.
Are we, we're on drive distribution still?
Yeah.
Lab 4?
Yeah, lab 4. It's, yeah, the one right that determine the plot.
Mm-hmm. Wait a minute here, let me just double check. I think I might have gotten rid of that. I just gotta double check which version I'm in here. This is the solution, okay. Let me just go ahead and stop the recording.